My name is Chris Nikolodakis, and I am a research associate at the Renewable and Sustainable Energy Systems Lab at Technical University of Crete. The focus and the goal today is to understand how we can assess macroalgae biorefineries sustainability in a transparent and scientifically defensible way. As an environmental assessment framework, we will use life cycle assessment, or LCA for short, and then we will briefly extend the discussion into social LCA. Here we have a quick overview of today's lecture. First, we will discuss why macroalgae biorefineries need sustainability assessment. Then we will introduce the ISO LCA framework, which includes the 4 steps: goal and scope definition, inventory analysis, impact assessment, and interpretation. After that, we'll focus on the choices that are especially important for macroalgae systems: the functional unit, the system boundaries, multifunctionality, and allocation choices. Then we'll move to inventory data, hotspots, and how these inventory flows are translated into impact categories through the life cycle impact assessment. Impact categories such as global warming potential. And finally, we'll look at what current study shows, and we'll close with some social LCA and key takeaways. Let's start with the basic question. Why are macroalgae biorefineries interesting in the first place? Macroalgae are interesting because they can act as a marine biomass platform for many circular bioeconomy pathways. They do not directly require arable land, and compared with many terrestrial biomass systems, they generally have lower dependence on fresh water and synthetic fertilizers. And also, during cultivation, macroalgae may also uptake nutrients from the aquatic ecosystem. However, the important point for biorefineries is their versatility, since depending on the species, composition, processing route, it can be used for food and feed, proteins, hydrocolloids such as agar or alginate, fertilizers, biostimulants, biofuel applications, and others. So macroalgae are not just one feedstock for one product, since they can support several product pathways. However promising this biomass characteristic may be, that does not necessarily mean that the full value chain is sustainable. And this is where sustainability assessment becomes necessary. Macroalgae may avoid some burdens of terrestrial biomass systems, but the full value chain may still have environmental and social implications. For example, cultivation and harvesting may require infrastructure, vessels, energy, and materials to operate. Fresh biomass is also wet and bulky, so it often needs transport, it needs reprocessing and preservation techniques. Also, then inside the biorefinery, we also have processing that may require heat, electricity, solvents, chemicals, and of course, wastewater treatment. The sustainability outcome depends on the actual system design, the actual cultivation method, the yields of the method of the processing, the overall logistics within the value chain, the processing technologies, and of course the scale of the production. And this is why we need the life cycle assessment, since it can help us move from a general sustainability claim to a structured assessment of where the burdens and benefits may occur across the life cycle of the production. What exactly does a life cycle assessment try to answer? LCA evaluates the environmental performance of a product system to a defined function. This is an important part because LCA is not asking for the impact of a material technology. It asks what environmental burdens and benefits are associated with delivering a specific function. So, for example, for a macroalgae system, we first need to know what function is being delivered. Is it producing just the biomass? Are we producing a high-value product? Are we producing agar or another product? And it basically LCA help us answer 4 practical questions. First, what processes are needed to deliver the function of the system? Second, what materials, energy, inputs, emissions, and waste are involved in this function? Third, which life cycle stages may drive the main impacts of the system? And fourth, how does one option may compare with another? So the value of LCA is that connects a defined function with a product system needed to deliver it. So, and then evaluates the environmental performance of that system across the life cycle. So to start this kind of assessment, LCA is a systematic method to evaluate the environmental impact of product, processes, or systems across their life cycle. And it's standardized under ISO 14040 and ISO 14044. And it includes four main steps. The first step is the goal and scope definition, which defines the purpose of the study, the functional unit, the system boundaries, and the intended use of the results. Then we have the lifecycle inventory analysis, where we quantify input and output flows of the product system. The third phase is the lifecycle impact assessment, where the flows from the previous step are translated into environmental impact categories, such as global warming potential. And we have the fourth phase, which is the interpretation, where we evaluate these results, identify hotspots, check consistency and uncertainty, draw conclusions, and of course, suggest improvements for the system. And as we see, this project is not purely linear, since interpretation can lead us back to revise the goal and scope, revise the inventory data, or the sensitivity analysis, etc. So the first phase, which is the goal and scope definition, is especially important because it determines what the study can actually answer. And this is where the study is framed. This phase determines what the LCA, for example, the purpose of the study may be a hotspot analysis, a comparison between alternative scenarios, a support for eco-design, or evidence for policy or communication. The function must also be defined. What product or service is the system delivering? In macroalgae systems, that could be the biomass itself. It might be bioplastic, it might be agar or fertilizer, or even a service such as nutrient removal. The system boundary then defines which life cycles are included in the analysis. Are we looking only at the cultivation system, cultivation and preservation method, or the full value chain of a biorefinery, and including the use of the product and the end of the life management? We also need to state any key assumptions to the system, allocation choices, avoided product credits, our data sources, any data gaps, and the limitations of the study. And also the target audience matters, because the study, for example, for internal process improvement, it may be framed differently from a comparative study used for public communication. So the goal and scope define the meaning and the limits of our results of the analysis. So once the goal and scope are defined, the next step is to build the inventory, the quantified flows that are needed to deliver the functional unit. In this phase, the product system is translated into quantified flows. In other words, we describe the system numerically, what enters and what leaves from our system, and which operations are involved. A typical inventory data in macroalgae systems may include the biomass itself, and materials, energy, fuels, water, and chemicals. Regarding the outputs, we have, of course, the products, any co-products that might occur, the residues, the wastewater, and any direct emissions. And of course, we have operations such as cultivation, harvesting, transport, process, drying, extraction, conversion, and other operations. Regarding the data sources, these may come from direct measurements, from the literature, any life cycle inventory databases, and of course, any assumptions if we have data gaps. The key point is that inventory is the data backbone of the LCA, and therefore, if our inventory is weak, incomplete, or poorly documented, it of course impacts our results and also the uncertainty of our results. So after the inventory phase, we move to the life cycle impact assessment, or LCI-IEA for short, and then to the interpretation phase. Since we have the flows from the inventory, such as energy use, fuels, materials, life cycle impact assessment translate these flows into impact indicators. So LCIA help us answer three basic questions: which impact categories are affected, how much each flow contributes, and which life cycle stages are hotspots within our system. For example, for greenhouse gas emissions, they contribute to global warming potential. Nutrient emissions may contribute to eutrophication, and so on. And interpretation help us answer whether the results are consistent with the golden scope definition, which inputs and assumptions drive the outcomes, and how robust are our conclusions. And this is important because macroalgae systems, our result may be sensitive to the functional unit, the boundaries, the allocation choices, and of course the energy mix and other inputs. So now that we have the LCA structure, we can state that the key question that will guide any macroalgae LCA. We don't ask simply, is this macroalgae system biorefinery sustainable? But a better LCA question might be, is this system sustainable to what, for which function, and under which system conditions? First, the key frame question is, what is the function of the system? Are we producing biomass? Are we producing a product? Second, what is the reference system or comparison? Are we comparing against a conventional product, for example, fossil-based plastic, synthetic fertilizers, fossil fuels, or other product pathway? Third is, which life cycle stages are we going to include? Are we looking only at the cultivation or also the processing of the biomass? And finally, which co-products, credits, and assumptions are considered? For example, how do we treat multiple products, the nutrient uptake during the cultivation, the avoided products, and allocation? So it does not give us a sustainability label in general, but a structured answer for a defined function, boundary, and comparison. So the first part of answering this question is defining the functional unit. It defines the quantified function of the system and becomes a reference for all the LCA results. This means that the results are not just reported of the impact of the system, but they are reported per functional unit. For example, per kilogram of dry biomass, per kilogram of alginate, per kilogram of agar, and so on. So this matters because the functional unit determines what systems can be fairly compared. If two systems do not deliver the same function, the results being compared directly may be misleading. So it also has to match, the functional unit has to match the goal of the study. If the goal is to compare packaging material, the unit should reflect the material and packaging function. So poor functional unit can hide or distort the product functionality. And before reading any LCA result, we should ask what this function is per watt. So let's look at a few examples of functional units. So this table shows why the functional unit need to follow the LCA equation. If the question is about how efficient is biomass supply, then a functional unit reflecting such as 1 ton of fresh or dry macroalgae may be appropriate, since the result tells about the cultivation and the harvesting performance. If the question is about the hydrocolloid production, such as agar, alginate, or carrageenan, then the functional unit should be related to the hydrocolloid product. For example, 1 kilogram of agar. In that case, we are interpreting the result as an ingredient or product comparison. For a protein product, if we have 1 kilogram of product that can be used, here we can also set the protein quality and the nutritional function compared to other protein sources. For bioenergy, the functional unit should reflect the energy service, such as 1 megajoule of fuel, that let us compare, for example, bioethanol in cars or biogas for electricity. However, this becomes more challenging when a macroalgae system delivers more than one function at the same time. So, in macroalgae biorefineries, this situation might be often more complex because the system rarely produces only one output, and a single feedstock can generate several type of outputs. We have, of course, the target products, which might be proteins, agar alginate, bioplastics, or other bioactive compounds. But through these value chains, we also have co-products, such as fertilizers, feed ingredients, and so on. And of course, we may have side streams, which include the residues, the wastewater, or other nutrient-rich fraction. So this is attractive from a circular bioeconomy perspective, because we want to use as much of the biomass as possible. But for LCA, we have a key question: how should these environmental burdens and benefits be assigned across these multiple outputs? And this is actually one key challenge in LCA for general, which is called the multifunctionality problem. And however, before we solve that problem, we need to define where the system starts and stops in our analysis. So after defining the functional unit, we need to define the system boundaries. The system boundaries tell us where the assessment starts and where we stop. And in this figure, we will see several common boundary choices. We have the four main life cycle stages. We have the raw material extraction, the production processing, the use of the products, and the end-of-life management or disposal between the transport stages. So, for example, a gate-to-gate study focuses only on one life cycle stages, usually in the production stage. A cradle-to-gate study starts from the raw material extraction until the product leaves the production system. A cradle-to-grave study continues further, including the use phase and disposal. And an even more novel concept is the cradle-to-cradle boundaries, which include the circular loops, such as reuse, recycling, or recovery. So, this is especially important for macroalgae systems, since if we only include the cultivation, we may stop at the raw material extraction and the transportation stage and see only the infrastructure and the fuel associated with these operations. If we include the preservation techniques, drying, etc., we will stop at the cradle-to-gate boundaries, and so on. So here we see the concept applied to a macroalgae value chain. At the left, we start with the cultivation, harvesting, and transport. If the system boundary stops here, the assessment mainly tells us about the biomass supply system. If we further extend the boundaries and include the preservation, then additional processes become visible, such as drying or other preservation techniques. If we continue further to the biorefinery, we include the extraction and conversion processes. And if we conduct a study in cradle-to-grave perspective, cradle-to-grave perspective, we include the product use and the end-of-the-life management of the product. So this is especially important if the system function is the materials itself or the product at the disposal. So the wider we go in the boundaries, the more stages we assess. However, this requires more data and assumptions for the analysis. So instead of using macroalgae biomass for only one product, a cascade system tries to recover several fractions in sequence. First, the biomass may be used for high-value product extraction, such as pigments, fucoidan, or other bioactive compounds. Then remaining fractions may be used for hydrocolloid or protein recovery, such as alginate, agar, carrageenan, or protein-rich fractions. After that, the system may produce materials or packaging products. And finally, the residues at the end of the value chain can still be valorized, such as to fertilizer or biogas. So from a circular bioeconomy perspective, it's attractive because we aim to use more of the biomass and reduce the waste. However, in LCA, it might create complexity since we have more processing steps, more products, and more side streams, and therefore more allocation questions. And this is why we need to discuss about the allocation and how we solve the multifunctionality in LCA. So when one system produces multiple outputs, in LCA we need to decide how we will handle these shared burdens. For example, in Macroalgae Biorefinery, the same cultivation system, the same biomass feedstock, contribute to several outputs. We may have alginate, we may have protein products, fertilizers, and so on. And through the ISO, we have mainly three approaches in solving the multifunctionality. We have the subdivision, where, if possible, we split the system into separate processes so that each product receives only the inputs and outputs, and of course the burdens related to its own process. The second is system expansion. Here the system is credited for replacing a conventional product. For example, if macroalgae residue is used as a fertilizer, the model may include an avoided burden for a conventional fertilizer production. And the third approach is, if we can neither solve it with system expansion, is allocation, where we distribute the burdens using a rule, for example, by mass, energy content, economic value, or another justified rule. And because allocation can strongly influence the impact of each product, the selected approach should be clearly documented. And this is where the sensitivity analysis may become important during the interpretation. So since we can use the sensitivity analysis to test whether the conclusion changes when important modeling choices or other influential parameters are varied. So if the conclusion changes when we switch from mass allocation to economic allocation, or when we vary in an important parameter like electricity demand, then the study should report that our system is sensitive to that input or assumption. So here we have these approaches visually. At the top, we have the subdivision approach, where the idea is to split the system into separate processes where possible. If process A is responsible for example, for alginate, and process B is responsible for fertilizer, we try to assign the relevant input and outputs separately for each process. In the middle, we have system expansion. Here, the system is expanded to account for what a co-product replaces. In this example, the Macroalgae Biorefinery produces alginate, and then the fertilizer as a co-product is treated as replacing a conventional fertilizer product. So the model can include an avoided burden for that replaced product. So, and at the bottom we have allocation. Here we are not splitting. The system is not separated. Instead, the set burden is divided between the products using a rule. For example, mass, energy, or economic value. And the key point is that these are not just accounting details, they can change the apparent impact of each product. So every LCA of a multi-product biorefinery should clearly state which approach was used and test whether the conclusion changes under the alternative choices. So now that we have defined the function, the boundary, and the multifunctionality approach, we can move to the lifecycle inventory. The inventory converts the defined system into quantified input and output flows, and these flows are related and normalized to the functional unit. Inputs in these systems may include biomass, materials, fuels, electricity, heat, water, chemicals, solvents, enzymes, and of course, we may include the infrastructure and the equipment. Regarding the outputs, we have the products and co-products, direct emissions to air, water, and soil, and the residues, wastewater, and any biomass losses. So this is where we collect the inventory data. And this may include the quantifying the vessel fuel needed for the cultivation system, the transportation flows, the usage of chemicals or other solvent used in the extraction processes. And it is a key step in LC studies, since that the quality of the inventory may strongly affect the reliability of the LCA results. And since if it's incomplete or based on weak assumptions, then also our result may be uncertain. So let's first look at the inventory for a biomass supply. We have the hatchery, cultivation, harvesting, and the transport processes. For cultivated macroalgae, this may start from the hatchery, where the inventory flows might include the electricity needs, lighting, and aeration. Then we move to the cultivation, where the inventory may include the ropes, the buoys, anchors, and fuel for maintenance and upkeep operations. During harvesting, we have the fuel use and, of course, the biomass yield of the operation. Yield is important because many infrastructure and operational burdens may be divided by the amount of the biomass produced. So the yield, of course, improves the efficiency of the system. And of course, we have the transport to the shore, where the fuel use and distance are the important variables. So different macroalgae supply routes have different profiles. For wild harvesting, for example, the main inventory drivers may be related to the operational parameters, such as boat fuel, the distance to the site, and of course, the seasonal availability. For offshore cultivation, we have the forest season, which includes the infrastructure such as ropes, etc., the maintenance strips, the boat fuel required, and of course the biomass yields. Regarding the onshore cultivation, we have more controlled variables, but we still require infrastructure such as tank or ponds, pumps, electricity, and water circulation. So the way the biomass is supplied, it can change the inventory flows and therefore the LCA result. So here we have an example of a study that compared wild harvesting, offshore and onshore cultivation of macroalgae. The study used a graduate boundary and the functional unit of 1 ton of fresh seaweed harvested. So the results refer specifically to the biomass supply. And in this case, the authors identify the fuel consumption and electricity as key drivers for these impacts. Also, the offshore systems require more controlled cultivation conditions. So we have more important variations. On the other hand, while harvesting has a different profile, which is linked to the harvesting operations and fuel use. This variation that we see in the onshore cultivation system for the ecotoxicity on freshwater ecosystem is mainly driven because the electricity supplied in the system is supplied from geothermal electricity, and is associated to the infrastructure and the drilling waste, which contributes to these results. This is a good example how the background data sets, for example, in this case, the electricity supplied, can strongly shape the LCA results. So after the biomass supply, the next important stage is the pre-processing of the biomass. Since it's the fresh macroalgae biomass may be wet and bulky, and of course, seasonally harvested. So this means that stabilization can strongly affect our results even before the extraction or the conversion begins. Common pre-processing steps may include the dewatering to reduce the water content, drying process for stabilizing storage and transport, the freezing of the biomass for preservation, and sealing as a lower energy alternative, the billing and size reduction, and also washing as a pre-treatment in case the biomass is processed as fresh. So the important point here is that pre-processing is not just a logistical detail, since it can shift the environmental profile of the whole system. For example, processes such as drying and freezing requires usually a lot of energy, and then this biomass may carry significant environmental burden before we even reach the biorefinery step. So when assessing about quality biorefineries, we need to ask not how only the biomass is processed within the facility, but also how it is cultivated and pre-processed before reaching the treatment. So here we have another study from Thomas and co-authors of Saccharina latissima cultivation and preservation study. Again, we have cultivate boundaries, and the functional unit was 1 ton of fresh kelp. The study compared several preservation options, including hang drying, air cabinet drying, and sealing and freezing. Key results is that preservation choice strongly affected the environmental profile of the system, especially in particular freezing and heated air cabinet drying processes had the greatest impact there, while in sealing and outdoor hang drying had much smaller impacts. And here we see how important the pre-processing steps are for our systems, and it shows that the environmental burden can be shaped before the biorefinery. So after pre-processing, we move into the biorefinery itself, where we may include extraction, conversion, separation, processing, purification, and waste treatment. Usually inside the biorefinery, we have a typical process such as for the pre-treatment, we have washing, milling, and size reduction. Then we have the extraction and conversion process that require heat, water, acid or alkalis, solvent, and enzymes. We have a separation process such as filtration, centrifugation, and membranes. We have the product recovery, where we concentrate the product, we dry and purify the final product, and the waste management process regarding the management of the residues, the wastewater, and any chemicals. So here we have a list of common hotspots that may appear across the macroalgae LCAs. One frequent hotspot is the drying or preservation, because fresh macroalgae may contain a lot of water content, and stabilization may require substantial energy use. Another one is the energy supply, since electricity, heat, and fuel, and the local energy mix influence our results. So, for example, the same process or biorefinery system may look very different depending on whether the energy system is fossil-based or based on renewable energy sources. On the biomass supply side, cultivation infrastructure may can matter. The use of ropes, buoys, anchors, and other components influence our results. Not only global warming, but also the toxicity parameters usually. Then we have the marine operations and logistics themselves, such as boat fuel, the transport distance, the handling of the wet biomass. Inside the biorefinery, important hotspots, of course, include the processing inputs, such as the solvents, the chemical used, and the extraction and purification steps. And of course, the yield and composition assumptions of may matter for the biomass productivity, the protein content, the carbohydrate content, and all affects how the environmental profile of the products is shaped per functional unit. So now that we have seen about the inventory and the common hotspots, we need to see how these inventory flows are become impact category results. So the life cycle inventories tell us what flows occur and at which life cycle stage. For example, we may have electricity used during the hatchery, diesel during the harvesting, sodium hydroxide during extraction, and so on. But life cycle impact assessment tell us what those flows may cause environmentally. So some inventory flows may be elementary flows, which means that these are direct exchanges with the environment, such as carbon dioxide emitted directly to air, the phosphates released to water, crude oil extracted from nature. And these are usually characterized directly into impact categories from in LCIA. However, other flows are in the technosphere and or product flows, and these are input from other human processes, such as the electricity production, the sodium hydroxide production, diesel, the solvent production, or other infrastructure related inputs. And these are not impact results directly. Instead, they are linked to lifecycle inventory background databases. For example, the electricity production, the chemical production, or food production. And these datasets are further linked to their own elementary flows, depending on the substances required to produce them or released during their processes. Then LCIA proceeds through three basic steps. We have the classification, where these flows are assigned to relevant impact categories. For example, the electricity production is maybe directly linked to the global warming potential in the future. For the nitrogen emissions are assigned to the eutrophication. Second, we have the characterization. What these elementary flows are converted into common indicator units. And then we have the aggregation, where these contributions are summed within each impact category. So, and as I said, these are linked to the inventory flows of the technosphere are linked to the background datasets, which contain their own elementary flows. And in this table, give us a simple example of that how the carbon dioxide emission and methane emissions can be characterized directly into kilograms of carbon dioxide equivalent emissions. For the electricity, this is linked to electricity production datasets. And of course, for the sodium hydroxide, this is linked to the chemical production dataset, which is further linked to multiple, maybe linked further to multiple impact categories. So this diagram shows the logic of one widely used LCIA method, Recipe 2016. On the left, we started from the life cycle inventor results, and these are the inventor flows that come from our model system. And then the RESP method convert these flows into 18 midpoint impact categories using specific characterization factors. Examples may include the particulate matter formation, global warming potential, marine ecotoxicity, and so on. And these midpoint categories describe a specific environmental mechanism. For example, global warming relates to the greenhouse gas emissions. Eutrophication relates to the nutrient emissions. Land use related to the land occupation or transformation processes. And RESP can also connect these midpoint impact categories to broader damage pathways, and then to endpoint areas, and then to the three endpoint areas of protection, such as damage to human health, damage to ecosystems, and resource availability. So we have a global warming potential as a familiar example of LCIA characterization. Global warming potential aggregates greenhouse gas emissions into the common indicators, which is kilograms of carbon dioxide equivalent emissions. Data is shown in the formula. So for each greenhouse gas, we multiply the amount emitted by its global warming potential characterization factor, and then we sum all the greenhouse gas contribution. So carbon dioxide, methane, and nitrous oxide can all be expressed in the same unit, though they don't have the same warming potential per kilogram emitted. So typical contributing flows in this, we have the carbon dioxide from the fuel combustion, the carbon dioxide from electricity production, and so on. So as I mentioned, global warming potential is not only about the direct emissions from the biorefinery itself, but also we have the upstream emissions from the electricity production, how the fuel was produced, the chemical and solvent production, and the infrastructure, since all these may contribute from their background life cycles and depending on our system boundaries. So after calculating the global warming potential results, we have the interpretation. In Macroalgae case, global warming potential results are often sensitive to several system choices. Usually, we have a strong contribution from drying and preservation methods. Second, we have the electricity and heat supply matters, since the same extraction or drying process may have a different global warming potential result depending on the energy mix. Third, we have the boat and fuel transport modeling choices, which can be important, especially for offshore cultivation. Fourth, we have the processing inputs such as extraction chemicals, solvents, which may contribute through their background production chains. For multi-product biorefineries, allocation among the co-products can also change which product appears to carry the burden. And of course, the assumption about the biogenic carbon and the avoided product can strongly affect the global warming potential. And therefore, during the interpretation, we need transparent assumptions and sensitivity analysis. Eutrophication is another important impact category for these systems. Eutrophication indicators describe the potential contribution of nutrient releases to excessive biological growth in aquatic systems. The main nutrient flows are usually nitrogen and phosphorus compounds, and nitrogen may appear as nitrate, ammonia, or other substances. Phosphorus may appear as phosphate or total phosphorus, and nutrient emissions can usually come from the wastewater, the processing residues, or other upstream background processes. In life cycle impact assessment, freshwater eutrophication is expressed as phosphorus-related equivalent as kilograms of phosphorus equivalent emissions. And for marine eutrophication, it's expressed in kilogram of nitrogen-related equivalent emissions. And macroalgae systems can involve a redirecting because nutrients can appear on both sides of the assessment. Nutrient emissions can be a burden, but macroalgae growth can also involve the nutrient uptake from the water. So this leads to an important modeling question. When should the nutrient uptake be treated as an environmental benefit? Since macroalgae can uptake nitrogen and phosphorus during its growth, and however, if the biomass is harvested, then part of these nutrients can be physically removed from the aquatic system, and this can be modeled as a benefit, but only under some conditions. First, the nutrients will be removed from the water body. Second, the biomass must be harvested, so the nutrients actually leave from the aquatic environment. Also, the nutrient removal service must be included in the system boundary, and of course, the crediting approach must also be transparent and justified. So the important is that the LC credit is a modeling choice, and we should therefore avoid saying that macroalgae can automatically reduce eutrophication in every LCA system. And a more accurate statement is that nutrient uptake can be credited as potential benefit when the context boundary and when the context and the boundary can support that modeling choice. So land use is one of the environmental categories often discussed in biomass system, but for macroalgae it requires careful interpretation. Since macroalgae reduces the pressure on arable land because they're cultivated in marine or aquatic environments rather than on agricultural land, this is one of the reasons that they are attractive compared to the terrestrial systems. However, low arable land demand does not mean that there are no spatial or ecological trade-offs. In conventional LCA, land occupation or land transformation may be characterized under land use indicators, but marine space occupation is not always captured well by these standard land use indicators. The macroalgae systems for offshore farms still require some space, and these may interact with the local ecosystems, fisheries, and coastal communities. And some of these effects are ecological, some may be social, and some may be governance related. So low land use does not mean that there are no spatial or ecological trade-offs. So what do current LCA studies show? The main conclusion is that macroalgae LCA show potential, but the results are, of course, system-specific. The product pathway strongly affect the hotspots. Biofuel pathway, hydrocolloid pathway, bioplastic or fertilizer do not have the same function, or to be more specific, the same processing needs. So therefore, we have variations in these environmental profiles. The cultivation, preservation, processing, and logistics all matter, since depending on the case, important contributors may include the cultivation infrastructure itself, the boat fuel required, the drying method, the heating requirements, and the other inputs such as chemical and solvents. So these results are sensitive to LCA modeling. Choices, especially the functional unit, the system boundary, the allocation approach, and any credits for co-products or avoided products. And finally, many macroalgae technologies are still early stage, so uncertainty and sensitivity analysis are essential at these low TRL levels. So here we have the main sustainability drivers across different product pathways. Each product pathway has a different function, and therefore different sustainability drivers. For biofuels and bioenergy, important drivers may include the conversion efficiency, the handling of the biomass, the transportation steps, and so on. And also the whether the product replaces the fossil energy, fossil fuel. For bioplastics and materials, the key drivers may be the extraction processes, the film fabrication, the drying steps, the end of the life management, and so on. For fertilizers, the processing burden may be relatively low, but also we have sustainable drivers such as from the transportation steps, and also if it substitutes synthetic or mineral fertilizers. For hydrocolloids and such as agar and alginate, these environmental profiles may be driven by the extraction chemistry, the heat requirements, the water use, the waste streams, and the process improvement in the future, and also the scale. And for bioactives and high-value compounds, we have, of course, the extraction efficiency, purification methods, solvent used, and so on. So one way to improve the biomass utilization, as we mentioned earlier, is to the cascade biorefinery concept. So cascade biorefineries aim to recover multiple products from the biomass. The opportunity is that we can extract high-value compound first, then valorize proteins, hydrocolloids, or other materials, valorize the residues for fertilizer, biogas, or other energy-related uses, where we improve the biomass utilization and reduce the waste, which fits within the bioeconomy concept. However, for the side, this creates a complexity side, since more products usually mean more processing steps, more co-products and side streams, and more allocation and system expansion choices. And for early stage designs, there is also a higher uncertainty because the data may come from lab scale experiments, the literature itself, pilot scale trials, simulations, or even assumptions. So cascade biorefineries are attractive, but from an analysis perspective, their performance depends on whether the additional product recovery justifies the extra processing, energy, chemicals, and so on. So this brings us to the prospective LCA and scale-up, because many of these cascade or multi-product systems are usually in still emerging technologies. So many macroalgae biorefinery systems are still emerging, so full industrial data does not exist yet. And this is where prospective LCA becomes useful, since it allows to evaluate technologies before they are fully commercialized, identify hotspots early in the development, support the code design, test future scenarios for scale, the energy supply and the supply chains. The pyramid on the right shows the basic idea. At lab scale, the data are often limited and uncertainty is high. At pilot scale, we start to get more realistic process information, but scale-up assumptions are still very important. And at the industrial scale, we usually have more direct measured data and lower uncertainty, although uncertainty never disappears completely from the systems. For macroalgae biorefineries, prospective results can depend strongly on the yield assumptions, the process efficiency, the upscaling method, the future of the electricity energy mix, the feedstock supply, the end of the life management of the product, and the substitution of the conventional products. So prospective LCA can be used as a design guidance under uncertainty, of course, and not as a final proof of concept for the sustainability at full scale. So here we have a concrete example of a prospective LCA applied to a seaweed-based bioplastic system. ALGAIA and co-authors assessed the biorefinery producing seaweed-based bioplastic. The boundary was cradle to grave, and the functional unit was defined as 1 kilogram of seaweed-based bioplastic film. The study considered two future scale-up scenarios, 4,000 tons per year in 2030 and 2 million tons per year in 2035. The key result here is that the best performing scenario in 2035 is 1.37 kilogram of carbon dioxide equivalent emissions per kilogram of the film when biogenic carbon uptake was accounted for. So for comparison region, the low density polyethylene alternative definitely was 3.6 kilogram of carbon dioxide equivalent emissions per kilogram of plastic product. And we observe that impacts decrease with the scale up, and mainly because the larger scale production improves the resource efficiency of the process itself. And also another important thing is that they also account for the carbon uptake during the cultivation of the biomass, and also the carbon release during the composting of the bioplastic at the end of the life. So up to this point, we have focused mostly on the environmental aspect. Of course, environmentalists tell us about the environmental burdens and benefits, but sustainability assessment might be broader than the environmental performance, which we may include also the economic and social dimensions. And this is where social LCA becomes relevant, since social LCA evaluates stakeholders affected across the life cycle of the system, any social risk and potential benefits, working conditions, health and safety, labor rights, local community effects, and value chain responsibility. For example, a Macroalgae biorefinery will perform well environmentally, but still raise questions about the worker safety, the seasonal employment, the local community acceptance, and so on. And below, we see the broader concept of life cycle sustainability assessment idea, where we have the environmental LCA, the life cycle costing, and social LCA. So even environmental LCA is necessary, it's not sufficient for a complete sustainability assessment of the system. So social LCA may evaluate its effects on people and organization across the value chain. For macroalgae systems, worker-related issues may include health and safety during the harvesting, the offshore cultivation, vessel operations, and processing. For local communities, relevant issues may include the coastal livelihoods, local employment, the community engagement, and the access to the marine space. For value chain actors, we may consider the supplier relationships, the benefit sharing, the fair competition, and the wealth distribution. And at the society and governance level, macroalgae systems may contribute to technology development and regional development. But of course, possible scale up and governance are still important. So the key message here is that macroalgae system can look environmentally promising while still creating social risk or unequal benefits. So here we have a macroalgae specific social, let's say, of macroalgae supply system. Paul and co-authors assessed the macroalgae supply system comparing wild harvesting and offshore cultivation. The boundary was Crowley Gate, and the factual unit was defined as $1 US generated during an 8-hour standard working day. So the key result in this case is that the wild harvesting had a lower social risk score. These scores are normalized. That's why we see in points in units. And the main risk identified include the occupational hazards, the injuries and fatalities, the forced labor, and discrimination. But the conclusions will be interpreted carefully, since the wild harvest may not be always socially better than offshore cultivation. And I would like to say that the broader takeaway is that the social say can reveal hotspots that environmental say may not capture may not capture, especially the risk related to the workers and their safety. So let's now close with some key takeaways. First, macroalgae may look promising, but it does not mean that it is sustainable. The sustainability depends on the actual system design, of course, the scale of the system, the energy supply, the logistics, the processing route, and the final product pathway. LC results are meaningful when the framing is clear. We always need to know this, the functional unit, the system boundary, the reference system, and the allocation approach, and any credits that were included in the study. The third is the hotspot that may be pathway specific. In some cases, cultivation infrastructure or board fuel may dominate. In others, the pre-processing may dominate, or even the biorefinery itself may drive the impact. So, due to the requirements of chemical and solvents. And so the fourth is the environmental performance is not the whole sustainability story, since social LC adds the perspective of the workers, the local communities, the value chain actors, governance, and benefit distribution. So the promise is that we should assess the biorefineries carefully and in a transparent way. So I'll end with a practical checklist. A robust assessment should clearly define the function of the system and the reference system used for the comparison. It should state the functional unit and the system boundary, because we determine what the result actually refers to. We should have also appropriate documentation of the inventory data and their quality. For the biorefinery, we also need to know how co-products are handled, the allocation choices, and the avoided burdens if we substitute a product. Then we need to check the selected impact categories and the LCI method, as well as how we will model the nutrient uptake and the biogenic carbon. Of course, we need to include sensitivity and asserted analysis and scale-up assumptions. And on the right, we have a diagram that summarizes that there is an iterative process where we define, at first we define the system, we model it, we characterize our impacts, interpret the results, and improve, and we repeat these steps for further improvement. So here are the list of sources used throughout the lecture. And thank you very much for your attention, and I will be happy to answer any question you might have. So let's see one question. If we are evaluating a new macroalgae bioplastics, will it be compared to fossil plastic? I think I saw in the case study earlier, it's wise to compare these bioplastic products to a reference that this bioplastic produced may substitute, since we find more sustainable ways to replace conventional fossil fuel plastics. Okay, I don't see any other question.